Hello friends, in this video we are going to discuss how to obtain the equation of motion of a compound pendulum using Hamiltonian's equation of motion. So here we're going to use the Hamiltonian's equation of motion in order to deduce the equation of motion of a compound pendulum. So before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel, right? And if you want to follow me on Insta, this is my Insta ID. Here you can see Ozaloikajit 123. This is the Insta ID. You can follow me on Insta. Okay, so now let's start. We have a rigid body. This is a rigid body. Okay, and it is capable of oscillating about this point, this fixed point through which the axis of rotation is passing, right? So this is the point, suppose O, right? And it is oscillating in a plane, right, in a vertical plane. So if you consider here, this is x-axis and this is y-axis, and right, so it is oscillating in a vertical plane, xy plane. Okay, let me imagine that way, right? So that the axis of rotation is along the z-axis. Let me consider that way, right? So then this rigid body, which is capable of oscillating in a vertical plane, then it is said to be a compound pendulum, right? Then this is said to be a compound pendulum. So it can oscillate this way, like this. Just wait. Give me a second. So this is the rigid body. This is oscillating this way, right? Like this. Okay. So now let us consider the center of mass of this is suppose C. This is the point. This is the suppose center of mass. Let me consider that way. This point C is the center of mass, and when it will oscillate from here to there, then it's gone up to this point. This is the center of mass, position of the center of mass. Now you see, this is suppose L. Let me consider this one is suppose L. Just wait. Let me use this. This is suppose the distance between the center of mass and the point through which the oscillation, the axis of rotation is passing. That is suppose L. L is the distance between the axis of rotation and the center of mass. So what is the height below the origin, below this point O, through which the axis of rotation is being passed, to this center of mass, to this center of mass. So let me draw the diagram here. You see, this is the point O, and this is the initial position of the center of mass at mean position. So it is oscillating, and it reached this point, suppose C, and if this distance is L, then this must be also L. But what will be the height below this O to this level? So that's going to be equal to, if we consider the angle through which it oscillates, that is suppose theta. In that case, this is the theta. So if this is the theta, then we can consider this one as base, and this is the hypotenuse, because side opposite to the right angle is hypotenuse. And if we apply trigonometry, suppose let me take this one as this is O, this is B, and this is C. Then from this triangle, sine theta will be equal to OB, sorry, not sin theta, let me take cos, okay, cos theta. In order to find the OB, let me take cos theta, which is base BO by OC. So here BO will be equal to OC into cos theta. So OC here, in this case OC is nothing but L. So we're gonna get BO is equal to, this part is equal to, you know, OC cos theta, that is L cos theta, right? L cos theta. So that's why here you see this height below this origin to this is your S, L cos theta. This is nothing but L cos theta, right? This is L cos theta, right? So hope you have understood this. So let me draw the diagram clearly, just wait. So here you see this is the rigid body oscillating this way. So this is the center of mass which is oscillating with the rigid body, right? This way, right? This is the center of mass C, and the distance between the center of mass and the point O through which the axis of rotation is passing through, right? This is so now just imagine that the axis of rotation is passing through this way, which is along z axis. Let's let me clean this here. I'm not going to draw the z axis because if I used to draw all the things, all the axes and each and everything, then that picture will be not clear, right? And the angle of oscillation through which it is oscillating be suppose theta, let it be theta, okay, let it be theta. Then this height below this point O to this center of mass at this position, when the center of mass is at this position, is given by L cos theta. That I have already explained how I have got this L cos theta, right? So let me write the origin here, just wait, let me write the O here, okay. This is L cos theta, that's what we have got. So why I have taken this, I will explain it later, right? So first let me write what I have considered here. So here I have considered a rigid body capable of oscillating in a vertical plane. Suppose it is xy plane about a fixed rotational axis. This is passing through the origin O, passing through O, and such body is called compound pendulum, okay. Let C be the center of mass of the body and M be the mass of the body, and OC, which is the distance from the axis of rotation to the center of mass C, which is equal to small l. This is given by small l, right? So, and just wait, let me consider the angle through which it oscillates, that is theta, okay. Theta be the angle through which it oscillates. Now you see kinetic energy. Kinetic energy is given by half mv square for a body moving with linear velocity v. So this is oscillatory motion moving with angle theta about some moving through angle theta about some axis of rotation. This is the supposed axis of rotation. In that case, so the role of mass in case of translational motion, the role played by the mass in translational motion, same role is played by the moment of inertia in this kind of motion, oscillatory motion, right? So in this case we can write the kinetic energy Ke, that's going to be equal to half the moment of inertia and the angular velocity theta dot square, okay, square of the angular velocity. So in case of translational motion, we used to take linear velocity, square of linear velocity, we used to take here, here angular displacement is theta and time derivative of theta gives the angular velocity, right? So hope you have understood this. So therefore, let me cut this. Therefore, the kinetic energy so let me represent it by the symbol T. That's going to be given by half I theta dot square, where I is equal to moment of inertia of the pendulum and theta dot is nothing but time derivative of theta, right? If you have two dots, then it's gonna represent second order derivative of theta with respect to t, right? So hope you know these things. Now let's calculate about the potential energy, right? Potential energy, we know potential energy is equal to mgh, right? So here you see the mass of this object, I have taken capital M here. So we can say that the mass of a body is concentrated at the center of mass here. So therefore m into g, mass into acceleration, force due to the gravitation force that must be acting downward in this direction, right? This is mg, direction of mg, mass into acceleration due to gravity, small g. Now here potential energy is mgh, so here mass we have taken m, g is small g, simply acceleration due to gravity. H is nothing but here this distance below the origin to the center of mass, this distance, that is L cos theta. But as we are taking this reference point O, and this height is below this reference point, so that's why we're going to take it negative, right? We're going to take it negative. Therefore potential energy, that's going to be represented by V, potential energy V, that's going to be given by m g into minus L cos theta, right? Minus L cos theta. So that's going to be equal to minus mg L cos theta. That's what we're going to have, right? So let's move on to the next page. Okay, let me take a new slide, right? So now we know that Lagrangian is equal to T minus V. If you don't know what is Lagrangian, Hamiltonian, then watch all the previous lectures. Okay, so I have given few links in the description box. First watch those videos first. Okay, so let's put the values of let me go back to the previous slide. So what is the kinetic energy? Let me copy this expression of kinetic energy and potential energy. Let me write this expressions in the new slide. Okay, let me copy this one. So here is the kinetic energy expression and the potential energy expression is this. So here is the potential energy expression. Okay, so let us put this here. So L, that's going to be equal to half I theta dot square minus V is nothing but minus mg L cos theta, right? So minus that's going to be plus, so simply we can write this way, plus mg L cos theta, right? So hope you have understood this. So let me take this as equation number 1, right? So now you see, just wait, give me a second, let me rearrange these things. Okay. Just taking too much space. So now what we're going to do here, first here you see, so let me write the relation between the Hamiltonian and Lagrangian. H, that is equal to summation Pz q dot z, right? Q dot z means time derivative of the coordinate minus L, time derivative of generalized coordinate. So qz, that means generalized coordinates. That means suppose we have large number of particles in a system. Okay, suppose each particle have coordinate x1, y1, z1, like this, right? So similarly, so here you see for different particles must have different coordinates. Okay, so those coordinates are represented by this qz, that is which are the functions of x, which is the function of x1, x2 dot 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 y1, y2 dot 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 z1, z2 up to n, if there are n number of particles, right? Let me consider that way. So and q dot z means this is nothing but time derivative of qz, right? So remember that. So now you see, so in this case, in the system, our generalized coordinate is nothing but theta. So here we're going to replace qz by theta. So we're going to replace q dot z by theta dot, right? And here pz, in this case, here pz is nothing but p theta, that is the angular momentum, right? So now here in this case we're going to write summation p theta dot minus L, right? So how to obtain the p theta, right? How to obtain p theta? So this is suppose equation number 2. Now p theta, so here you see momentum, mass into velocity. So this is suppose x-axis, a particle is at the position x at time t. If x, the position is the it is a function of time t, then we can write that momentum p, this linear momentum p, v can be written as x dot, that means v is equal to dx by dt, right? We can write it. But in this case, so here the compound pendulum is oscillating this way, right? So instead of x, our coordinate is now theta, right? So that is theta. So that's why, so in this case we're going to write p theta, that's going to be, and the role of the mass will be played by moment of inertia, then angular velocity, that theta dot. And this is in terms of Lagrangian, it is in terms of Lagrangian, that p theta is given by del L by del theta, right? Del L by del theta dot, that is given by del L by del theta dot. Okay, so now just wait, let me clean these things. So del L by del theta dot. So if you differentiate this equation number 1 with respect to theta dot, so this is function of theta, not theta dot. That's why that's the derivative of this part with respect to theta dot, that's going to be 0, right? And derivative of this, that's going to be equal to half into I is constant here, 2 into theta dot. So sorry, 2 into theta dot, 2 cancels. So we can write I theta dot. That's what we can write. So hope you have understood this. Now you see, let me use this result in equation number 2. Okay, so let me use this result in equation number 2. So here we're going to write this one here, since, so if you use this result here, summation I theta dot into, again this theta dot is there, minus L, that's what we're going to have. So and here you see one more thing. So let's put the value of L as well. So let's put this one as well. So I, that's going to be theta dot square minus, so if we put the value of L from equation number 1, then what we're going to have, So this is what we're gonna have, right? So using 1, right? So here, just wait. Actually, I should write this one. This is gonna represent the moment of whole system. That's why I'm not gonna write the summation here. Okay. So hope you have understood this. So the momentum of the whole system will be represented by p theta. Okay. So let me write here p theta. Okay. So hope you have understood this. So that means we're gonna write. We have replaced here. Just wait. Let me clean these things. What we have done here, we have replaced the summation of pj and qj dot by p theta dot, right? So hope you have understood this. So now let's simplify this. Then what we can have here, so I theta dot square minus half I theta dot square, that's going to be minus mgl cos theta, right? And if you subtract this two, then you're going to have half I theta dot square minus mgl cos theta, right? That's what we're going to have. Okay. So hope you have got it up to this point. So now you see, from this relation, what we can write, let me use this, let me write this step in the next page. Just wait, let me copy this and let me go to the last page and the next page. So here, so we have already got that p theta is equal to I theta dot, right? And from here we can replace the theta dot, right? We can replace the theta dot by p theta by I, right? So if we do so, then what we're gonna have, theta dot is replaced by p theta by I. So here we're gonna have square mgl cos theta, since, let me write this one, since theta dot is equal to this, right? So if you simplify this, I gonna cancel I square. So what we're gonna have, this I by p square theta by I square, that's gonna cancel the square. So that's why what we're gonna have, we're gonna have p theta, p square theta by I minus mgl cos theta, right? That's what we have got. Now Hamiltonian's equation of motion. So for to understand this, you have to study about the Hamiltonian's canonical equations of motion, right? So I have given the link in the description box. Okay. According to Hamiltonian canonical equation of motion, we get qj, or you can write qk dot, qj dot, okay, del h by del p j, and pj dot is equal to minus del h by del qk, right? So these are the Hamiltonian canonical equation of motion. So I have already made a lecture on this topic, Hamiltonian's canonical equations of motion. Just click the link given in the description box, okay? Then it will help you to better understand, okay? So here in this situation, here this qj will be replaced by theta, qj dot will be replaced by theta dot, right? And pj will be replaced by p theta dot, okay? So then what we're going to have, so Hamiltonian's equation of motion, for theta and p theta are, what we're going to have, theta dot, that's going to be equal to del h by del p theta, right? So now if you differentiate this is ace, right? If you differentiate this with respect to p theta, then this part gonna be 0 because this is not a function of p theta. And if you differentiate this part, then what you're gonna have, half into 2 p theta by I, 2 gonna be cancelled, so you're gonna have p theta by I only, right? So hope you have understood this. So that's why theta dot gonna be equal to p theta by I. That's what we're gonna have, right? And then if this is the case, from here what we're gonna have, p theta, that's gonna be equal to I theta dot. And if you differentiate it again, right, if you just wait, let me adjust it, right. Just wait. And if you differentiate it again, then what you're gonna have, p theta dot, that's gonna be equal to I theta double dot, right? If you differentiate it again, then you're gonna get this. This is suppose equation number 2. And what we're gonna have, and canonical equation, Hamiltonian equation for p theta, that's gonna be p theta dot, that equal to, according to this equation, we're gonna have minus, instead of qk, we're gonna have theta here, right? And if you differentiate it with respect to theta, this part is not function of theta, that's going to be 0. If you differentiate it with respect to theta, then what you're going to have, so this cos theta, that's going to be minus sin theta, right? So this minus, that's going to be plus. Again there is minus, so again it's going to be negative. Finally that's going to be negative, because derivative of cos theta with respect to theta, that is minus sin theta. And this minus going to be plus, and this minus again is going to be minus, right? So hope you have understood this. This part going to be 0 as not function of theta, so we're going to have minus mgl sin theta, right? We get this. So hope you have understood this. So now this is also p dot theta, right? P theta dot, not p dot theta, p theta dot. So from these two equations, from 2 and 3, what we can write, from 2 and 3, what we can write p theta, this p theta can be replaced by this value, right? So then we're gonna have I theta double dot is equal to minus mg L sin theta, right? And if you simplify it, then you're gonna have theta double dot I theta double dot minus, that's minus becomes plus, mg L sin theta is equal to 0. Now let me take a new slide. Okay, so if we divide both sides by I, then we're going to have theta double dot plus mgl sin theta by I is equal to 0 divided by I, that's going to be 0. Now you see, for very small angle of oscillation, for very small angle theta, we can write sin theta is approximately equal to theta. That's why this equation becomes this, mgl theta by I is equal to 0. So this is the equation. This is the equation of motion of a compound pendulum. So hope you have understood. So thank you for watching. See you in the next video.